assistant professor at Northwestern University. Actually, Marcus Buehler, who was my doctoral advisor, was supposed to give these talks, but unfortunately he can't be here. So I'm here to basically give 6 lectures on what he would be talking about, which is atomistic modeling of biological materials, and starting from molecular scale going up to microscopic scales. Just to give you a basic idea, I work mostly on atomistic and multi-scale modeling of biological materials, as I said, a little bit on nanomechanics, biomechanics, and mechanics and energy and environmental sciences. So I'll talk mostly about the general computational mechanics approach we take to studying these difficult problems, and then also a little bit about applications. So the first lecture I had is very broad. It's talking about modeling and simulation and understanding dynamics of materials at these small scales. And then I'll talk about the molecular dynamics method in the second lecture today. And then in the third and fourth and upcoming lectures, I'll talk about mechanics of protein materials and some of the theoretical and computational approaches we have to understand these materials. So the first lecture is mostly about what we do in modeling and simulation, and kind of our perspective on how to approach these problems. If I think about it, there's 3 approaches to scientific research. One is doing actual experiments. So if you want to look at a problem like diffusion, you could actually do the experiment in the lab and look at the time you need to reach equilibrium. And you can also look at it from an analytical perspective and try to come up with a mathematical formula that will explain the diffusion process, such as Fick's diffusion law and so forth. These approaches both work very well for diffusion, and you can also do something like a computational study or a computer experiment, where you basically run a simulation of how the particles float around in this glass, and then you can essentially predict how fast the diffusion is going to occur. So these are sort of complementary approaches. Computational approaches are really nice when you can't have a very simple analytical solution, or you want to interpret the experiments a little bit better. So this is what we call sort of computational science and engineering, and it's different from computer science in the sense that you try to solve physics problems, and it does have a lot of computer science in it because you have to implement code and so forth. But this is what we call computational science. So as I talk more about computer methods, it's nice to talk a little bit about the brief history of computing. Well, it's not so brief if you go all the way back to ancient civilizations. The abacus is basically the basis of all the computing devices we have. Then we have, until 17th century, not a lot of development, but we had a sliding rule. And the 19th century was really when computing started to become involved in machinery. And one of the key events that actually catalyzed this was the growing number of population in the United States. So it became really difficult to calculate the census, the number of people in the country. You were doing the calculations by hand, and it was obvious that it would take you more than the time for the next census event to be able to collect all of the data and count it. So they started to make simple machinery that would basically give you the census data more quickly. So that's the basis of the modern computer, where Boolean algebra, punch cards, etc. were developed in the 19th century. And then one of the key events was, of course, the Second World War, where the computational power increased massively because we needed to crack codes and heuristic tables and these kind of things. So that's when we started to go into what we call a large-scale computing era. And then this trend kind of reversed back, and now we have our personal computers. It's more of a distributed phase. We don't have to go to a big building with our punch cards anymore. And we have these little nice computers and even cell phones that can do quite sophisticated calculations. But then we see also something that is happening on parallel, which is what we call supercomputing or cloud computing, where you have again these humongous facilities where you can do a lot of calculations even from your cell phone. And essentially there's a lot of debate as to which direction the future of computing is going to go. Is it going to be more of a localized kind of approach where we have these laptops and so forth, or is it going to be almost all cloud-based computing and so forth? So it's an interesting perspective on computational engineering and what kind of resources we will have in the near future. One of the interesting things here is that computing power has been increasing exponentially, which is called Moore's law. This enables us to solve very complex problems day by day. And since I work mostly on atomistic modeling, I'd like to give the perspective from our viewpoint, where basically, if you look at the number of atoms you could treat in a molecular simulation, in the 60s it was about maybe 100 atoms, which is very small. Whereas now we can really look at billions and billions of atoms. This looks great, but we don't know if this is going to be a continuing trend. That's number one. Two, if you think about Avogadro's number, it's 10 to the power of 23, so we're still orders of magnitude smaller than any kind of nanoscale system. So then there are a lot of challenges that we need to meet and theories that we need to develop to be able to make predictions that are relevant to microscopic systems. So if we look at the history of molecular computation, molecular simulations, some of the key developments here were around after the Second World War, when we had these quantum computers, but we didn't have much use for them anymore. So a lot of these computers were used for understanding molecular phenomena that weren't experimentally easy to observe at the time. So this is sort of where many methods like the Metropolis Monte Carlo method came about, and there were studies on radiation damage to systems, and then application to complex fluids, and so forth, and even more recently, implementation of quantum mechanical methods into computational approaches, such as Pugno. And nowadays, we can basically study anything from a polymer to a protein to a lipid using these tools, and try to understand some of the molecular mechanisms that pertain to their mechanics. So this is sort of the focus of my research. And this is basically the computer called MANIAC, which stands for Mathematical Analyzer Numerical Integrated and Computer, dating back in the 50s. So a good question here is, of course, what kind of methods do we have, and how many of these methods are at the same scale we can do experiments and compare. And there's many different approaches, of course. Many of you are probably familiar with continuum models, such as finite element modeling. Then we have quantum mechanical methods. And in between there, we have a wide range of particle-based methods, such as molecular dynamics, or reactive simulations, or mesoscale models, coarse-grained models. Professor Gao talked about them a little bit in the context of carbon nanotube interactions with cells. So these are all the methods we have across the scales computationally, and then we also have a lot of complementary experimental methods to validate some of the approaches we take in computation. From the modeling and simulation perspective, it's good to make a few basic definitions as to what we mean by a system, model, and a simulation. So a system is essentially a finite collection of entities that are positions with respect to time, varying with time and exhibiting a behavior as a whole. In the case of physical systems, the position really means where an object is spatial. But this is a sort of a confining definition of what we mean by position. Because we could use the same techniques for social systems, such as how people interact or how financial systems evolve and so forth. And these are basically, again, positions, but just not spatial. It also relates to preferences of people. And a lot of the methods that have been used to simulate molecules have also been used to simulate behavior of people, which is an interesting analogy in that sense. And then model, of course, you're familiar with this, is a simplified idealization of a system and its constituents. We've used this for structural models of high-rises and so forth. And a simulation is, of course, imitating the behavior of a system in a virtual environment. So trying to do something that you can do experimentally in the computer. Of course, this has to address a particular need. For instance, you need to solve a problem that you cannot solve. And so I wanted to put a picture of Chicago and the subway system and the railroad system here, which is extremely complicated. This is where I live, basically, so I'm very familiar with how difficult it is to get from point A to point B. And if you look at it from a high-level perspective, it looks even more complicated than it is. So what is a model in that sense? This is what Mike actually said. It's an idealization. You don't have to stick to all of the details. You have to keep the details that are really important for what you need to do. And that's basically what a railroad map essentially does. The scales are not necessarily correct, but we know how to get from point A to point B in a clever way. And then the basis of simulation is, of course, refers to the procedure of solving the governing equations that results from the model development. So this is basically to predict how we go from state A to state B. And when you Google simulation on the web, you get a picture like this. World War I horse simulator. This is not really what we mean by simulation from a computational perspective. It's more neither this one, the Microsoft Flight Simulator, which actually does have some physics in it, but what we really mean is more of a Navier-Stokes equation kind of problem, where we look at computer simulation and we look at mathematical operations that describe physical phenomena. So one interesting thing when you look at system model simulation definitions we've made is that a lot of systems are really multi-scale in nature. If you look at a liquid in a container, it's really a definition of the microscopic particles, and you can see that they behave in a certain way at the macro scale as well. Same with social systems. You always have at least two different scales, and you can look at emergent phenomena from one scale to the other. And if you look at computation, it's actually a very short history. I mean, we've had experimental techniques for centuries, but with computation, the predictive power has only recently come to life. And we've used it for many different problems. Even in financial engineering, 70% of all transactions are now made with a computer, which I think is a huge number and probably relates to why we've been having so many issues in the recent past. In this sense, we can do a lot of recent things, developments with computational power, but it's at its infancy. If you look at timeline in technological development, what we observe is that we've come from macroscopic systems to smaller systems, such as biological systems and nanotechnology, and now we're looking at things in the scale of angstroms, which is much smaller than what we used to do. So this again goes back to the idea of multi-scale modeling paradigm, where we need to incorporate a lot of these quantum level details or molecular level details into higher level ideas. And this is sort of one of the key ideas now in computational mechanics. Then the goal of the computational scientist is essentially through simulation we try to understand the mechanisms of nanoscale phenomena. We can do these without destroying samples. We can be able to come up with some analytical descriptions and look at scenarios that don't even physically exist. For instance, we could look at a material that doesn't exist in nature and then observe a phenomenon and then try to mimic it in the lab. And this is something that can be exploited further. And then you can also potentially investigate many different drugs and mechanics problems without actually trying to test them. One aspect that we can think about is, of course, can we use computational mechanics in treating issues like cancer and cardiovascular disease, which are the first number 2 killers in the developed world. So, I'll talk a little bit about some of the modeling that pertains to these kind of problems. Whenever I don't know what to talk about, I Google it on Wikipedia, and basically it gives me a list of things that I can say about dynamics in this case. I want to briefly discuss that a lot of the phenomena we observe at the small scale are really dynamic, so nothing is static anymore. Everything has a probability of happening, and this sort of is an important aspect at the molecular scale. As you can see from the number of methods described here, many of them pertain to molecular systems, and it seems that dynamics is an important concept at the molecular scale. But what's the starting point of talking about dynamics? Historically, it goes back to the case of Newton. We know the basic law of universal gravitation. The basic idea here is that two bodies interact with each other by a gravitational potential. And this is the same concept that I'm going to talk about when I talk about molecular dynamics. Two particles will interact with each other with potential that describes the chemical interactions between them. So classical mechanics in this sense is quite accurate for describing the motion of a system of particles, and this is the basic idea in molecular simulation, that we can describe certain things with a classical description and then try to look at the emergent phenomena that comes from these basic chemical interactions. Of course, this doesn't work if we need to look at, for instance, the motion of electrons and so forth. So that's one of the limitations of the methods we use. And then you might be very familiar with its context, the context of dynamics. In engineering, when we use dynamics, we simplify a lot of systems, such as a high-rise building, wireless non-mass and spring kind of systems. It's the same kind of approach at the molecular scale. It's not really that different, but I'll talk a little bit about how the mathematical operations that we do can be different in computation and implementation. And since most of our mechanicians, a lot of the times we're interested in the material state, which is essentially a dynamic process, and there's many different time scales that can be involved in this. For instance, if you look at an earthquake, it's a process that often happens in the scale of minutes, or a collapse of a building, whereas something like bone fracture can be happening very instantly at a very fast rate. So there's a lot of time scale issues that are relevant to fracture events. And one thing that we can talk about is this atomistic viewpoint of fracture, that fracture is basically breaking and sliding and shearing of bonds at these small scales. And what this means is that connectivities of the particles change with respect to time. So nothing is essentially connected to each other permanently, but everything is sort of seeing each other as time evolves. And this understanding this phenomena is really key to understanding how a material fails. So this is one of the things that we'll talk about more when we talk about applications. The other difference between looking at macroscopic systems and small systems is that everything feels everything, which is basically the basis of chemical laws. The second thing is that because you have temperature, things are rarely static, so they're always vibrating and floating around. And this is very relevant to what we talk when we talk about fracture, in the sense that a bond breaking is very related to how hot the system is or how these vibrations are occurring. So when a system is very hot, it's easy for the bond to break and the atom to escape. And this is related to what happens, for instance, with gas. So this is important for the case of fracture, which Professor Gao also talked about, because you have temperature dependence and stochastic events that occur, which basically are important to consider, especially as you go into softer materials, so biological materials. This consideration of the lifetime and temperature effects is very important. And it's also important for the inverse problem of how you form materials. So we can talk about simulations of self-assembly, how materials come together. And in this case also, the approach is very different than what we had in top-down. In top-down approach, we basically have a need, and we pick the material to be able to satisfy that need. In biological approach, it's entirely different. We define the chemical interactions, and the chemical interactions evolve into sort of a structure that serves the function. And if it doesn't serve the function, then it basically is eliminated through the survival of the fittest or any other approach. So this is sort of the difference, and the key implication of that is that when you look at biology, structure and materials are kind of merged together. You really have the chemistry of the material, and then it's almost like the material is the product at the end of the day, and there's no real distinction between what we call structure and what we call material. So that's one of the key aspects of these systems. There's many examples of these self-assembly processes that are interesting in biology. So these are some of the things that we can do with approaches like molecular simulation. We can really study how a complicated material such as a protein will fold onto itself and create this structure. And this is always governed by the chemical interactions and also the environment that the protein is involved in. So this is an example of the folding of a small peptide. And this is, of course, what we call a lipid bilayer. So this is what constitutes a cell's membrane, for instance. And if you look at these events, these are very complicated, dynamic simulations where a lot of things are evolving. So it's very hard to capture some of these effects with a a simple continuum description, such as finite element methods. We'll talk about some of the advantages of using these particle methods, such as molecular dynamics. And then the question, of course, is, that's great, we can look at these at the smaller scales, but can we really connect this to the macroscopic behavior? So, for instance, if you look at a problem like diffusion, can we really link the individual trajectories or individual events that we observe at the smaller scales into macroscopic phenomena, like macroscopic behavior? And this is one of the key concepts that we have in molecular dynamics. So a single state from a simulation is not necessarily representative, but if you look at averages over time, then that can be very relevant. And this is something we call ensembles. So you might have very different trajectories when you look at the individual motion of the particles. They might go at random places, but their overall behavior has to be the same if you are in equilibrium with the environment. So this is one of the distinctions between some of the continuum approaches we have and some of the molecular approaches. So just before we get into really the details of molecular simulations, I want to talk about a little bit about the advantages of why we do molecular simulation as opposed to other methods. First of all, we can obtain reliable information about a system when an overall analytical description doesn't exist. For instance, if you know the microscale laws, you can predict the emergent behavior for the overall system. And this is the basis of finite elements as well. I mean, we know the solution to the finite elements, but we don't know the solution to a high-rise system, so we use these finite elements to solve a more complicated problem. The same issue with molecular dynamics, just different type of treatment. And then one can use computer experiments to gauge existing approximate theories and improve them. And this can shed light on experiments where mechanisms and trajectories, for instance, cannot be easily observed. And then you can also consider that in many experiments, your conditions may not be very well defined, whereas with computation modeling, you know exactly what you put into the system, so you can relate that to some of the things you observe. And then one of the key considerations is that if you consider the Moore's law and expect that it's going to hold in the next 10, 20 years, what you can do today on a workstation can be done in a cell phone in 10 years or 5 years or even shorter. So this means that we can probably solve much more complicated problems all the time. This was actually someone had mentioned this to me when I started my PhD, because I wrote computation, and somebody was saying the first simulations that you do when you start will be done in a matter of seconds by the time you graduate. So this was a sort of a thing that indeed is true, that the methods and the time scales evolve very fast. And this is one of the things that I would have to consider in computational work. And then the nicest thing about it is that computational approaches are cheap, remotely accessible, and transferable, storable, fast, scalable, and so forth. So this really is a nice aspect. Then we need to talk a little bit about some of the important issues with simulations. At the end of the day, what you get is just numbers. So the analysis becomes the center point of the research. And the interpretation and presentation of vast numerical data, thousands and billions of atoms, can really be challenging in itself. So there's a lot of people who look at just the visualization aspects of simulations. So this is a very demanding area of research as well, if you're interested in more computational mechanics research. The other thing is, even if you observe a novel phenomena, it will need to be experimentally validated in many cases. For instance, we can talk about hypothetical materials, but until the material exists, there's not that much value sometimes with what we can say with simulation. So, but it can really direct a lot of the experimental efforts in that sense. So that's one of the key advantages of our approaches. And how we build our models of assumptions may govern the validity of our observations. Of course, this is another issue. And many of the widely used techniques, approaches are still in their infancy. So there are problems that we can't accurately model with what we have today. So there's a lot of focus on how to improve the current models and so forth. And then there's also different scales of observation when you do molecular dynamics versus experiments. So So smaller time scales, smaller length scales often limit applicability of the results. And we're going to talk about what kind of methods there are to get around these problems and make predictions that are more reliable than just one observation. So I think that's basically all I have as a very, very broad introduction to molecular methods and molecular dynamics in particular. If you're interested in this area, I don't know how many of you have background in, do any of you have background in molecular dynamics or computational methods in general, like finite elements? Okay, so I mean, a lot of probably more continuing people than molecular mechanics people here. So I think the next stage will be quite introductory in the sense that we'll talk about basic principles of molecular dynamics. And these are some of the recent, or not so recent, books that are in the field that are also very helpful. So a lot of these slides are basically from a course called Computational Nanodynamics that I teach at Northwestern, which is a graduate level course, but undergraduates also take it. So I try to keep it as general as possible. And a lot of the students use these tools towards research at the end of the course. So they use molecular dynamics to attack some of the problems or train the finite element simulations or these kind of things. So this is why it's sort of a general description. But the idea is to basically talk about it. And if you have any questions, I'd be happy to answer them with this basic introduction. Any questions? No questions? Okay, so this is the basis of the molecular dynamics approach. And now we're going from very broad computational perspective into the specifics of the molecular dynamics approach. Okay, so recall that we talked a little bit about Newton's laws of motion. So every object in a state of uniform motion tends to remain in that state until we apply external force. And this is very basic. We have F equals ma, which is really the basis of any classical system that you can describe. And what we see here is, of course, to be able to do this, you need a system of particles. So what we do is basically atoms behave like classical particles, interacting with each other by certain potentials. And each particle in the system feels the net potential that is caused by the presence of all of the other atoms in the system. So it's almost like celestial mechanics, but instead of gravitational interactions, you have more complicated chemical interactions. And then the objective of this approach is, of course, we want to be able to see the trajectories of all of the particles as a function of time in a specified time interval. And then what we have is the classical equations of motion, F equals ma, and then if you have more than 2 particles or 3 particles, the general solution for many interacting particles, it doesn't exist. So this is why we need a computer model to be able to predict the time scales and predict the time evolution of these systems. And then what we do is basically we need to predict positions, velocities, and accelerations as a function of time. So then one can think of a simple algorithm to be able to do this. I have the initial conditions, so initial positions and initial velocities. And what I want is the positions at the next time step. And then the simplest way to do that mathematically is do a Taylor expansion. And now you can basically have r t plus delta t, which will be a function of velocity and then the time difference.